Does this mean that the glaciers are overdue? Is winter coming? To answer these questions, we need to understand what triggers the march of the glaciers and why they eventually retreat. In fact, we know the broad answer to this, even if the details are under debate. Earth's motion around the sun changes, and with it the intensity and distribution of sunlight. It was Serbian scientist Milutin Milankovic who realized that the gravitational tug of Jupiter and Saturn would lead to 3 periodic shifts that might explain the enormous climatic swings of the Quaternary period. These are the Milankovitch cycles. Let me summarize. 1. The elongation, or the eccentricity, of Earth's elliptical orbit shifts from almost completely circular to somewhat more elliptical in a 100,000-year cycle. At the absolute maximum eccentricity, Earth's most distant point from the Sun, the aphelion, is about 13% further than the closest point, the perihelion. One hemisphere will experience summer at aphelion and winter at perihelion, and milder seasons all around. That's the north at the moment. The southern hemisphere is closer to the sun in summer and further in the winter, so more extreme seasons. However, the difference in sunlight intensity due to this difference in distance from the sun is much less than the simple difference due to the seasons themselves, so this shouldn't be a huge effect. 2. The pointing of Earth's axis precesses. It rotates 360 degrees over approximately 26,000 years. In addition, the long axis of Earth's elliptical orbit also precesses. Together, these two effects define where in the orbit the seasons occur. They combine to produce a 21,000-year cycle called the precession of the equinoxes. So eventually, the North's mild perihelion winter will turn into a cold aphelion winter. And 3. Earth's tilt changes. Our spin axis is now tilted at 23.5 degrees relative to the axis of our orbit. This obliquity oscillates between 22.1 and 24.5 degrees over 41,000 years. High obliquity means more extreme seasons, but it's low obliquity that ultimately leads to a colder global climate, because then the highest latitudes, where glaciation begins, never get much sun.
Over Earth's long history, there have been dramatic changes to our climate. The ice ages have come and gone. And what's surprising is that there's a strong pattern that explains why ice ages happen when they do. This is called the Milankovitch cycle. Named after Milutin Milankovic, his theory explains how the Earth's climate changes over hundreds of thousands of years. His theory is based on 2 key ideas. First, the Earth's climate is strongly affected by how much sunlight the northern latitudes receive during the summer. Second, this amount of sunlight varies based on changes in the Earth's orbit and rotation. Why are the northern latitudes so important? It's because of ice. When sunlight hits the ground, most of the energy is absorbed as heat. But if the ground is covered in ice, most of the light reflects away because ice is white. This creates a positive feedback loop. Ice forms when it's cold, but ice also reflects light, making it colder, which forms more ice. So ice is really important for climate. The northern and southern hemispheres both contain lots of ice, but there's more ice in the north because there's more land. Land has a lower heat capacity than water, which means that water doesn't change temperature as easily as land does. This is why coastal regions are generally more mild and why ice forms more easily on land. Just look at the difference between the northern and southern hemispheres. In the south, there are ice caps that grow during its winter, but not nearly as much as they do in the north. During the winter, the land above the Arctic Circle is covered in darkness, experiencing twilight 24 hours a day. It's very cold, and lots of ice forms during the winter. And this is true no matter what's going on with Earth's orbit. The key variable here is how much ice melts during the summer. This depends on how much sunlight there is during the summer. Now, you might think that this doesn't change, but it does. Milankovitch showed that over hundreds of thousands of years, the amount of summer sunlight can shift plus or minus 15%. This can bring ice ages. This can end ice ages. How can the amount of summer sunlight be changing? Well, first, the distance from the Earth to the Sun is changing. And second, the Earth's tilt is changing. The Earth's axis is currently tilted at 23.5 degrees, but this changes. Other objects influence the Earth gravitationally, nudging its tilt up and down. Every 41,000 years, it cycles up and down. When the Earth is more tilted, there's more sunlight during the summer. More summer sunlight means that more of our ice melts away. With less ice on the ground, less light is reflected away, giving us a warmer climate. Earth is unusual in that its tilt doesn't change very much.
The polar ice caps are melting. But guess what? They're not. NASA says so. In fact, according to new research, Antarctica has gained so much ice, it's overbalanced for the ice that the continent has lost. From 1992 to 2001, the continent gained more ice than it lost to melting, 112 billion tons every year. So wait, if global warming is real, how come Antarctica's ice is thickening? Okay, so I apologize for the slightly clickbaity headline, but to be honest, whether or not scientists are lying to us that's a real question. But did anybody lie? No, internet buddies, they didn't. In fact, this ice research is consistent with other papers climatologists have released. In 2013, NASA's Earth Observatory announced Antarctic sea ice had set a new record. Another study said the same thing in 2012. There's more sea ice now than the 1981 to 2010 average levels. I know what you're thinking, because I thought the same thing. If the globe is warming, how can Antarctica be gaining ice? Okay, so don't believe the hype. Research still states unequivocally Antarctica is losing ice at a fantastic rate across most of the continent. Ice has increased in East Antarctica and the interior of West Antarctica. But other parts of Antarctica are still melting a lot. A lot. So let's be clear, gaining sea ice at this point is actually bad. Yeah, you heard me, it's bad. Well, there's this annual cycle of sea ice melt and freeze, where the ice is at its lowest point in February and March and thickest in September and October. According to a new, not yet published paper from a NASA Goddard scientist brought to our attention by Discovery News writer Patrick J. Kiger, global warming and climate change are actually increasing sea ice. See, melting glaciers have been depositing fresh water into the Southern Ocean. And if you think back to 7th grade science, which freezes first, salt water or fresh water? Exactly, fresh water does. Salt water has a much lower freezing point. It can get colder before it will freeze. This paper's conclusion is the top layer of water surrounding Antarctica has been diluted by the massive freshwater melt from the ice shelves, and therefore it freezes more easily today than in previous decades. This accounts for the increase in sea ice. The 2012 study found a 1.5% increase in sea ice accumulation over the decade. And this isn't the only paper that reaches that conclusion. According to a 2012 paper in Nature, which also predicted this effect, it is happening even more quickly in the real world than it did in their models, which is even more troubling. In a few more years, the new author, James Hansen, said, this will of course be clearer because the sea ice will continue to expand.
We know that sea levels around the world are rising, and current thinking is that part of that sea level rise comes from melting ice in Antarctica. But one recent study from NASA scientists says that may not be the case. Antarctica is a big place, roughly the size of the US and Mexico combined. So as you might expect, changes in its ice are not uniform across the entire continent. And nearly all scientists agree that ice is being lost from the western part of Antarctica and along its peninsula. On the eastern side, ice is actually being gained. But where this study is different is they measure that gaining of ice along eastern Antarctica is outpacing the loss on the western side. What's behind this addition of ice? It's snowfalls that started becoming heavier around 10,000 years ago. The scientists know this by looking into ice core data. Why is this important? It would mean that Antarctica is not contributing to sea level rise. But before you go buying up coastal property, there are several things to consider. We are already observing the effects of sea level rise in places like Miami, where routine high tides are inundating parts of the city which never saw water before. Also, even though this gain of ice has been occurring for thousands of years, it may not be around to stay. In the next 20 to 30 years, the increasing rate of loss in Western Antarctica could outpace the gains in Eastern Antarctica. Bottom line, there is still a lot we need to learn about how Antarctica is reacting to climate change. But you can be sure sea levels will continue to rise, as Antarctica has only made up about 8% of the sea level rise that we have observed.
Yeah, thanks, Joe. Well, what's happened is that there's been another great big iceberg that's carved off from the ice sheet, as we've heard. It's from an area called the Brunt Ice Shelf. It's on the exact opposite side of Antarctica from where the Australian Antarctic Territory is. It's in the Weddell Sea area. It's been an iceberg that scientists, particularly at the British Antarctic Survey, have been monitoring for some time, probably over about the last decade, and it's just carved off within the last couple of days.
Yeah, and we're just seeing some really dramatic shots of the crack. Can you tell us how long that line is? Like we've heard it's about 1,300 square kilometres, a whole piece. But is that, just to give people a better idea, how long is that crack that runs across Antarctica?
Well, it's an ice shelf on Antarctica. So these big slabs of ice form when snow kind of accretes on top of the continent, and over hundreds of thousands of years they flow out towards the ocean, and then they meet the ocean and they want to start to float because they're thin enough, and they form these huge expanses of ice that are actually over the top of the ocean. These cracks can be, tens and tens of kilometres long actually, and this particular one is massive. Yeah.
How big is this compared to other recent carvings?
It's a big one. Yeah, like you said, I think it's roughly 1,200 square kilometres.
Yeah.
In September 2019, the Amery Ice Shelf, which I've just talked about a couple of times already, it carved an iceberg from an area we called the Loose Tooth because it looked a little bit like a wobbly tooth from space. That one was 1,600 square kilometres. That one was also incredibly big. The icebergs of this size don't come along that often, and that's why it's very interesting to watch what this will do. It's a big tabular iceberg, we would call it.
Yeah. Is this part of a regular natural carving process for parts of Antarctica, or is it happening more often now than it has before?
We can't say for this particular iceberg, for any one particular iceberg, because, like I said, the predictability of them is so difficult. I mean, you've got to think about iceberg carving as kind of being like earthquakes, in the sense that we know there's something that's going to happen, but the exact timing of it and how it exactly happens is very uncertain. And so for this particular iceberg, it's part of the natural variability, I'd say. Big ones happen less often than little ones. Little ones happen more often. And there's a size range of icebergs that are being carved from Antarctica all the time.
Why doesn't the sun set in Antarctica for half the year?
G'day Grace, you might not know this, but the Earth's on an angle. So in the summer, the South Pole, or Antarctica, is tilted towards the sun and receives the direct sunlight from the sun for about half the year. 6 months later, the Earth is rotated to the other side of the sun and we're in winter. So down here in Antarctica, or the South Pole, we don't receive any light at all for nearly 6 months.